In this video, I'm going to discuss the idea behind what an augmented matrix is, and I'm going to look at elementary row operations and introduce the concept and idea of them. Now, point I'd like to note for this video is that I'm going to stick with 2x2 systems. However, the theory in the materials here can be extrapolated out into larger matrix systems, so 3x3, 4x4, etc. And they follow the same generic rules. The only difference is there's more terms within the matrices and the sizes are bigger. But 2x2 systems are the best way to introduce them because they help us to understand it on a fundamental level before we build on it and introduce higher levels of skill. The first question we have to answer before I talk about elementary row operations is, what is an augmented matrix? Well, we know a system of equation can be represented in the form AX equals B in terms of matrices. So it would look something like this. So our ABCD, an XY and an EF. In this system, if we relate it back to this, our A is a 2x2 matrix of coefficients of X and Y in our system. The matrix X is a 2x1 matrix of our variables, often referred to as a vector in this case. And the B is a 2x1 matrix consisting of the right-hand side of the system of equations. So for example, this one here would represent AX plus BY equals E, and CX plus DY equals F. So that would be the system represented by these matrices here. Now what we're able to do is compact this idea even more and combine B into a matrix with A and X to make the augmented matrix. And the augmented matrix looks this style. Now, one thing you'll notice is that I don't include the variables, so i.e. in this case the X and the Y. That's because what we're doing is relating the coefficients to the solutions, because we're assuming the X and Y are there and we know what column relates to what variable, and it gives us a platform to work with and solve multiple equations at the same time. So for example, for this one, we know this column here refers to the X coefficients. This column here refers to the Y coefficients. So as long as we bear it in mind, we don't need to worry about writing X and Y down every single time. So this contains all the information in the system and the set of equations we've got, and this can be used to get a solution. Now it's very similar to simultaneous equations. The good thing about it is that we can then start to build it up to equations that involve more than two variables. However, when we've got the matrix written in this form, so our augmented matrix, what we have to be able to do is manipulate it, manipulate the values, and do elementary row operations on it in order to be able to take the matrix and put it in a format we want so we can get the solutions. Now when it comes to row operations, we have to understand what they are and what the row operations we're able to do consist of. So first thing we need to know is that when we're solving our system of equations, there are several alterations we can make that can be used to produce the same solution. So the first is that the order of equations can be switched. So what that means is, if I look back at the previous example where I had A, B and E, and I had my C, my D and my F, what that means is I could swap the two equations round. So I could rewrite it as C, D, F and A, B, E. And it should still produce the same solution overall. An equation within the system can be multiplied by a constant. So what that would mean is that would be the same concept as if I had an equation, let's say X plus Y equals 2, and I was able to get a solution for that. I should get the same solution as 2x plus 2y equals 4, as long as it relates to this one, and as long as the second equation still gives me a solution consistent with what I got here. So imagine I had a second equation that was x minus y equals 4, and I kept that second equation, x minus y equals 4, as my second equation there. All I did was multiply the first one by the constant 2. This would still give me the same solution overall for x and y. What we can also do is take one equation and it can be added or subtracted from another. So one of the rows can be added or subtracted from another row. What this then allows me to do is combine rows in ways that for example, I can get rid of one of the coefficients, say C in this case, such that it makes the equation easier to solve because I eliminate one of the variables from within that system of equations. So I could eliminate this, get C equal to 0, and then all I'd have left is the y, and I could just read off a solution for what y is. Now, a key thing to remember is that no matter what transformations we do, we want to make the system into a format that is quick, easy, and efficient to solve, and makes our life as easy as we possibly can. So when we're doing alterations as elementary row operations, what we have to do is we've got certain notations that we can have that allow us to keep track and record what row operations we've done. So here's a few that we've got here. So this first notation here, what that's telling me is I'm taking row 1 and row 2 and I'm interchanging them. So I'm swapping all of row 1 with all of row 2. Now a key thing to note is that you swap the entire row. You don't just swap a part of it. If you move one row, you have to move every element in that row and switch it with the corresponding element in the other row. Second one here is what I'm telling you is that row 1 becomes A times row 1, where A is just some coefficient, some constant number. So I'm manipulating the row and I'm making it bigger if A is bigger than 1, or smaller if A is less than 1. Or I could even go negative and invert the signs of the entire row. Third notation I've got here is that row 1 becomes becomes row 1 plus row 2. So I take row 1 and I combine it with row 2, and that then now becomes my new row 1. And again, this holds because we're combining and being constant and consistent with combining the x parts, the y parts, and the solutions together, or any other variables as well, obviously. 3x3 matrix, we've got z's as well, etc. Now these are just written on their own, simple ones on their own, however we can combine them. So this one that I've got here, written in this shorthand notation, is telling me that row 1 is becoming row 1 take away 5 times row 2. So I'm going to take row 2, whatever the values there are, I'm going to multiply it by 5 and I'm going to subtract each of those values from the associated value in row 1. So we can manipulate the matrices using these elementary row operations and get it to how we want. Doing this allows us to solve and work with the system of equations in a much quicker, efficient and effective manner. Let me show you an example. So let's imagine I've got a system of equations here. What I want to do is use elementary row operations and the augmented matrix to solve this system of equations. So I've got this here. What I can do is construct this into the form AX equals B. So for this, for AX equals B, so my A is the coefficients of each of the terms here. So I've got 3, -2, 7, and 3. The x1 is a vector which has my variables in it, so my x and my y. And that equals B, which is the solution, is a 2x1 matrix, written like that. Now what I do is I can combine the constant matrices such that I can get my augmented matrix. So my augmented matrix for this one would be 3, -2, 5, 7, 3, and 4. What you'll find is putting a line down there shows you where the coefficients of the variables finish and the solutions to the equations begin. And remember what each of the columns are associated with. So we should know that this is associated with the coefficients of x, this column here is associated with the coefficients of y, and this column here is associated with our solutions. So now what we can do is use elementary row operations in order to be able to manipulate this and get a solution that we want. Now what you'll notice is if I take this row here, so my second row, and I multiply it by 3, and I then subtract 7 of row 1, and I say, right, that's then going to go into row 2, what I can tell you is that this is going to eliminate my x variable. Because if I take 3 of this row here, so I'll have 21, 9 and 12. I'll take away 7 of the first row here, I'll get 21, so those two will disappear. I'll get minus 14, and I'll get 35. So if we just focus on the first part here, manipulating them, so let's say we're going to do 3 of row 2, and we're going to do 7 of row 1. I could rewrite the augmented matrix as 21, negative 14, 35, and I'd have 3 in my row 2, so 21, 9, and 12. So there we go, just like that. So manipulating it this way, to multiplying both rows, gives me one of the coefficients equivalent. Because what I notice now is that if I do row 2, take away row 1, and put that into where row 2 is, what's going to happen is these are going to disappear. So what that then means, the top row I'm doing nothing to it, so that's going to stay the same. So I'm at 21, negative 14 and 35. However, what I'm going to do for each element in row 2 is subtract the corresponding element in row 1. So I'm going to do 21 take away 21, which gives me 0. I'm going to do 9 take away negative 14, so minus minus becomes a plus, so I get 9 plus 14, that gives me 23, and then I've got 12 take away 35, which gives me minus 23. And I can then do it there. Now at this point we're actually able to read off our solution, because if you think, remember that we said that this is associated with x, this is associated with y. This top equation tells me I've got 21x take away 14y equals 35. Now that looks as if it could be a lot more complex than what was up there. It's a heck of a lot more in it. However, my second equation tells me that 23y is equal to negative 23. So I can get my solution for y like that, straight away. So if 23y is negative 23, y is equal to negative 1. I can then take that negative 1 and substitute it into this first equation here to solve. So what I can say is 21x take away 14 times that negative 1 is equal to 35. So I've got 21x. So 14 times negative 1 is negative 14. Minus minus becomes a plus. So plus 14 equals 35. And this is an equation I'd now expect an S1 to be able to solve. Shift over the 14. I get 21x is equal to 21. X is equal to 1. So for this system of equation, for both of these to hold true at the same time, I know that x is 1 and y is negative 1. So similar fashion to simultaneous equations, the difference being I'm representing it as an augmented matrix to begin with and using these row operations in order to be able to solve. It's the same premise as before. The difference being is that now I've got a method and a technique I can take and extrapolate and expand onto equations with 3, 4, 5 variables, because I'll then have the corresponding number of equations. For example, I need 3 equations to solve for 3 variables, 4 equations to solve for 4 variables, 5 to solve for 5. And the augmented matrices, if I use them in this fashion, with those, will make it a lot easier for me to manipulate and solve, and much quicker and more efficient.